Welcome back to another Explainer, everyone. I am seriously so excited about today's topic because we are going to completely shatter the way you look at the solid objects all around you. Okay, let's dive right in. Today we're uncovering the hidden movement of atoms. We're talking about solid-state diffusion. And by the end of this Explainer, you're going to understand the invisible atomic traffic that literally powers our modern world, from the cars we drive to the smartphones sitting in our pockets.
To hook you right away, think about a beautiful, high-performance Corvette. The beating heart of its power transfer is a case-hardened steel gear assembly. Now, what's really fascinating here is that the incredible durability of this car's transmission isn't just about the raw steel itself. It's actually the result of carbon atoms being intentionally forced to migrate into the solid steel surface to harden it. I mean, it looks like a solid, impenetrable piece of metal, but at the atomic level, it's basically a sponge that has soaked up carbon. How is that even possible?
To answer that, here's our roadmap for today. 1. What is solid diffusion? 2. How atoms actually move. 3. The rules of the road. 4. The heat factor. And 5. Building better microchips. Stick with me through the atomic theory early on because we're going to see a massive technological payoff at the end.
So, let's jump straight into Section 1. What is solid diffusion? And more importantly, the illusion of scale.
It's totally human nature to look at a block of metal, or a piece of glass, and think of it as completely static and dead. But that's an illusion of scale. To really grasp this, picture what we call a copper-nickel diffusion couple. Imagine we take a pure block of copper and clamp it tightly against a pure block of nickel. Now, if we heat them up for an extended period, those atoms don't just stay put. Over time, the copper atoms naturally migrate right into the nickel lattice, and the nickel atoms wander over into the copper. That previously sharp boundary, it becomes a blended alloy. Solids aren't these static walls. They're actually bustling crowds.
Let's define exactly what's happening there. That process is called interdiffusion, which, simply put, is atoms of one metal migrating into another metal. This causes visible compositional changes, like creating that blended copper-nickel alloy zone we just talked about. But there's another type too, called self-diffusion. This is when atoms of the exact same type exchange positions within a pure metal. Self-diffusion is happening constantly inside every piece of pure metal around you, but without us ever seeing it. I mean, a copper atom swapping places with another copper atom doesn't really change the macroscopic makeup of the material, right?
Let's move to our next section, Part 2, How Atoms Actually Move Inside Crystal Lattices.
We know atoms move, but how? These solids are dense, tightly packed crystal lattices. How does an atom push its way through a seemingly solid wall of other atoms? Well, there are two main mechanisms. First is vacancy diffusion. This relies on an empty spot, a vacancy, in the crystal lattice. An adjacent atom basically jumps into that empty hole, which in turn leaves a new empty hole right behind it. It's exactly like one of those sliding tile puzzles where you move the squares around using that one single empty space on the board. The second mechanism is interstitial diffusion. Here, a much smaller atom doesn't bother waiting for a vacancy. It simply squeezes itself into the tiny empty spaces, the interstices, between the larger host atoms.
So the absolutely crucial point here is comparing these two. Vacancy diffusion relies on host atoms swapping places with adjacent empty lattice sites. Interstitial diffusion relies on smaller atoms squeezing between the host atoms. Think of an incredibly crowded room full of adults. If an adult wants to move across the room, they have to wait for an empty spot to open up and step into it. That's vacancy diffusion, and as you can guess, it's pretty slow. But if a small child wants to cross that same room, they can easily duck and weave through the gaps between the adults without needing a whole empty space to open up. That's interstitial diffusion, and because of that, it happens much, much more rapidly.
But wait, it's not quite a free-for-all in there. For any atom to make a move, two very strict conditions have to be met. First, an empty adjacent site must exist, either a full vacancy or a tiny interstitial gap. Second, the atom needs sufficient vibrational energy to break its bonds with its current neighbor atoms and physically force its way through to the new spot. If both of these conditions aren't perfectly met, that atom is utterly trapped in its lattice.
All right, now that we know the mechanisms, let's explore Part 3, the rules of the road and controlling that atomic traffic.
Engineers don't just rely on trial and error. They use precise mathematical frameworks to control this traffic perfectly. These frameworks are known as Fick's laws. Fick's first law describes steady-state diffusion. In really simple terms, it states that the rate of diffusion is directly proportional to the concentration gradient. Atoms naturally want to flow from an area of high concentration to an area of low concentration. It's exactly like a ball naturally rolling down a steep hill. Fick's second law, on the other hand, deals with non-steady state diffusion. This is much more common in reality, where the concentration gradient actually changes over time as the atoms pile up or deplete.
So what does Fick's first law look like in action? Well, imagine steady-state diffusion across a thin metal plate. You've got a high pressure of a gas on one side and low pressure on the other. If you map that out, it forms a perfect linear slope. The concentration profile is entirely constant. The exact mass of atoms entering the left side perfectly matches the mass exiting the right side. It's just a continuous, steady flow down that concentration gradient hill.
But in real manufacturing, say when we want to harden that Corvette gear we looked at earlier by stuffing carbon into the steel, we aren't usually dealing with a simple steady flow through a plate. The concentration is changing constantly as the steel fills up with carbon. So, the multi-million-dollar engineering question becomes, how long will this diffusion process actually take to reach the exact depth and hardness we need?
To answer that, we turn to Fick's second law. And, okay, I know, partial differential equations and Gaussian error functions sound incredibly intimidating, but stick with me, you absolutely don't need to be a math major to understand what this represents. This equation is simply the ultimate cheat code. By plugging in the starting concentration, the surface concentration, and the desired depth, engineers use this exact math to calculate the precise number of hours, minutes, and seconds a piece of steel needs to sit in a furnace to harden perfectly.
Speaking of sitting in a furnace, let's pivot to part 4, the single most critical variable in this entire explainer, the heat factor, and pressing fast forward. I want to read this quote directly from our source material because it is just staggering. Temperature has a profound influence on the coefficients and diffusion rates, increasing approximately 6 orders of magnitude. 6 orders of magnitude. That means raising the temperature of a metal from, say, 500 degrees Celsius to 900 degrees Celsius doesn't just speed up diffusion a little bit, it can make the atoms move 1,000,000 times faster. Adding heat is literally pressing the fast-forward button on atomic movement.
When you actually plot the diffusion coefficient against temperature, the resulting lines are incredibly steep. And because we usually look at the reciprocal of temperature, as the material gets cooler, those diffusion rates absolutely plummet downwards. The second you remove the heat, diffusion effectively slams into a brick wall and just stops.
Why does heat matter so much? Because of something called activation energy. This is the critical energy barrier required to produce the diffusive motion of atoms. Remember back in section 2 when we said an atom needs sufficient vibrational energy to break its bonds? Well, this is the math behind that rule. Every single material has an activation energy threshold. Heat provides the thermal energy necessary to vibrate those atoms violently enough to shatter their current bonds and jump into the next lattice site. High activation energy means you need an incredibly hot furnace to get anything moving.
Now, let's bring it all together for part 5, building better microchips through solid-state diffusion. We've zoomed way into the lattice and looked at the math, but let's zoom back out to the macro world. Manipulating this microscopic atomic traffic isn't just for hardening gears, it is the fundamental process that allows us to build modern electronics. Let's look at semiconductor integrated circuits, the microchips in your computers and phones. Creating the tiny electrical pathways inside a silicon chip relies entirely on solid-state diffusion, and it's done in 2 highly controlled manufacturing steps. Step 1 is predeposition. The silicon chip is exposed to a gas full of impurity atoms, which diffuse into the very top layer of the solid silicon. Step 2 is the drive-in. The gas is removed and the chip is hit with high heat to transport those trapped impurities deeper into the silicon to create a specific distribution.
If we map out the concentration profiles during this 2-step dance, it's pretty wild. During that first predeposition step, you get a huge spike. The impurity atoms are highly concentrated right at the surface, but they don't go very deep at all. Then comes the drive-in step. By applying high heat, using our Fick's second law cheat code to calculate the exact time, by the way, engineers meticulously push those impurity atoms much deeper into the silicon. This lowers the surface concentration, but spreads the atoms out to perfectly form the electronic pathways of the microchip.
And the scale of this whole operation is absolutely breathtaking. We're talking about tiny aluminum interconnects on an integrated circuit chip that are maybe 4 micrometers across. To put that in perspective, that is a tiny fraction of the width of a single human hair. By using diffusion to embed impurities and then laying down these microscopic metallic roads, engineers can connect millions of electronic devices on a single chip.
But there is an incredible irony here.
We just spent this whole explainer learning how we use solid-state diffusion to build the chip. But once the chip is built, diffusion becomes the ultimate enemy. Aluminum is specifically chosen for these interconnects because its diffusion rate in silicon is extremely low. If they used a metal that diffused easily at operating temperatures, the atoms from the pathways would slowly bleed into the silicon over time, ultimately short-circuiting and destroying the very chip we just built. Engineers literally have to choose materials to stop the diffusion process they just utilized.
Which brings us to our final thought. The next time you pick up your smartphone, remember that it's not just a solid piece of silicon and metal, it's a frozen snapshot of meticulously orchestrated atomic traffic. But it leaves us with a fascinating question. As our microchips shrink further and further, approaching the size of the atoms themselves, how will the hard physical and mathematical limits of solid-state diffusion dictate the future boundaries of our technology? It's definitely something to think about. Thank you so much for joining me on this explainer, and keep learning.